Okay, in this lesson, we're going to be looking at the purposes of using stoichiometry. We're going to be looking at limiting and excess reagents. And so we're going to start off with the concept of just making double burgers. So when we make a double burger, we know that we need a bun and we need 2 patties. And that's how we're going to make our double burger. If we were to have 1 bun and 2 meat patties, we would end up with 1 double burger. If we had 2 buns and 4 meat patties, we would have 2 double burgers. If we had 2 buns and 2 meat patties, we would be limited by the amount of meat patties that we have, because we have said in our diagram that we need 1 bun and we need 2 patties, and so we would only be able to make 1 double burger, and we would say that 2 meat patties are the limiting cause of why we can only make 1 double burger. Now, if we went to the extreme and we said if I had 2 buns and 1 million meat patties, I could still only make 2 double burgers because I need 1 bun and 2 patties, and now I only have 2 buns. And so we're limited by the amount of buns that we have. This is really important. Limiting and excess are terms that we use when we're describing how a reaction is going to go forwards, or if it's not going to create enough product. Limiting reagents, so it's the reactant that determines how much product can be formed. That's always what happens in a reaction, and the excess reagent is the reactant that's in the larger quantities. So the limiting reagent, the reaction can only happen for as much as that bare minimum reagent is in there. So that's kind of the same idea as saturation, where if I'm mixing sodium chloride and water, the water can only hold so much salt before the salt stays as a precipitate. It's the same kind of idea. There's some steps that we follow. Again, we always write a balanced chemical equation. And before that, we're always going to balance our compounds. Okay? Once we do that, we need to calculate each reactant down to their moles. So we have to figure that out. And typically we're given a mass. So we would find moles by going mass divided by molar mass. But we can do it using concentration and volume as well if we're given 2 solutions. Then we have to look at this concept of evening out the number of moles. And so we need to look at, when we write a balanced equation, and we'll see in the next example, but if we're looking at if we're looking at a question like this, we don't typically write the 1 in, but I'm doing it for show. When we look at a question like this, it looks like sulfur would be the limiting reagent because there's only 1 mole of sulfur in that entire reaction. And it looks like copper has way more to give to that reaction than sulfur does. But what happens is, when we even it out, once we find the moles for this one, by going mass over molar mass, and same with this one, we go mass over molar mass, what we do is we even out this entire reaction, and we take this number of moles and we divide it by the coefficient. Same with this one, we would take this number of moles and we would divide it by this coefficient. And then we'll start to see which one is truly the limiting reagent. Once we even it out and we find the lowest one, whichever one of these two values is the lowest, then we're going to take our original mole calculation This is key. Lots of people forget this step. We're going to take our original calculated moles and we're going to go through the rest of the equation, making sure that this one was the from the lowest or the limiting reagent. Okay, let's put that into practice. When 80 grams of copper When 80 grams of copper and 25 grams of sulfur react, which reactant is limiting? And then what is the maximum amount of copper sulfide that can be produced? Now I know that a lot of people had a question on the word amount, and I always told you that that would relate to the number of moles. But in this particular case, this question is asking you for mass. Okay? So what's the first thing we have to do? We have to write a balanced reaction. When copper is reacted with sulfur, we will get copper 1 sulfide. There's a couple of things that we need to remember here. Sulfur in its elemental form is actually an S8. And copper sulfide, this is specific to a 1 plus charge, and this is a 2 negative charge. So copper would have a 2 subscript behind it. Then we always write down our known information. And then step number 2 says that we need to calculate the number of moles for each reagent. So if we remember that moles is equal to mass over molar mass, we would have 80 grams over 63.55 grams for copper, and we would have 25 grams, not over 32.06 grams or 07 grams, but by 256.56 grams per mole, because we need to multiply it out by 8. And we would see that we would get 1.25 moles here, and we would get 0.0974 moles here. The third step says that we have to even it out. So we need to take our 1.25 moles and we need to divide it by, oh, we forgot to balance our equation. So here I have 8 sulfur, so I'll put 8 here. I see that I end up with 16 copper, so I'll put a 16 here. Oh, Miss Pyre missed the very first step. Okay, and we're going to divide this by 16 because we take this coefficient. There's 16 moles in the entire reaction, so we have to divide this out by 16. Then we're going to take the 0.0974 and we're going to divide it out by 1, because in the entire reaction there is 1 sulfur compound, 1 mole of sulfur in the reaction. And so what we do then is we'll see that we'll get 0.0786 moles here, and we'll get 0.0974 moles here. Now we can compare them because this is for the entire reaction on an even playing field. That's why even was put in brackets. And we see that the less reagent is the copper reagent. This is where 90% of people make an error. What we want to do is we want to be able to use our moles to compare to a mole ratio to be able to calculate out a mass. What we have to do is we have to go back to the original mole value that we calculated. So we need this value here. This is limiting. So we're going to use the 1.25 and all of the decimals that go with it. So you have 1.25 moles of copper. Now we're going to look at the mole ratio. So when we look at this, there is 16 coppers and there is 8 copper sulfides. So this is typically step number 3 that we've been doing for most stoichiometry. This part here is step number 2 that was done in step number 2. And then we need to get to mass. So mass is in step number 4. Mass is equal to your moles multiplied by your molar mass. And our molar mass of copper 1 sulfide is 159.17 grams per mole. And we should get for a value 100 grams of copper sulfide. When we do a unit analysis, we can see that we have copper taken care of there, and we have our moles taken care of here, and we're left with copper sulfide, and grams to get grams of copper sulfide. I'll just show you quickly. Initially when I did this, even Mrs. Pyre made that mistake. Look what I did. I put in the calculated for the reaction, not for the original mole amount. So it's something you need to pay attention to when you're working on doing limiting and excess reagents. Example number 2. You're supplied with 9 grams potassium chloride and 6.5 grams of silver nitrate. So we're going to figure out the mass of precipitate formed when these two chemicals react. So let's look at what we're making. So KCl and silver nitrate. We're going to get silver chloride and potassium nitrate. Sorry, these should be... When we go to our solubility table, we're going to see that we're going to put these into solution. We're going to see that silver chloride is a precipitate. It's slightly soluble, whereas potassium nitrate is extremely soluble. We need to make sure that we balance our equation out, and these are all 1-to-1, so this is balanced. We have 9 grams of potassium chloride and 6.50 grams of silver nitrate. It's asking us what is the mass of the precipitate formed when these two chemicals react. So first things first, we need to figure out our moles of each component. So we're going to go 9 grams divided by 74.55 grams per mole. And we're going to go 6.50 grams of silver nitrate divided by 169.88 grams per mole. We should get a value of 0.120 moles here, and we should get a value of 0.0382 moles. This is step 2. This was step 1. Step 3 is to figure out which one is limiting. When we go back to the original equation, this has a coefficient of 1 and this has a coefficient of 1. Well, 0.120 divided by 1 is 0.120, and 0.0382 divided by 1, 0.0382, which means that this is the limiting reagent. This has the least amount of moles, so this is going to be the driving factor. Step 4 is calculate out what it's asking for. It's asking us for the mass. And we need to remember to take our original calculated number of moles, so 0.0382 moles of silver nitrate. We're going to do our 1/2 ratio. I have 1 of silver nitrate. I have 1 of silver chloride. Then I'm going to multiply it by, this was step number 3 in our typical pattern. This is step number 4 in our typical pattern, where we figure out that mass is moles multiplied by molar mass. So we're going to multiply it by 143.32 grams per mole of silver chloride, and we should get a value of 5.48 grams of silver chloride. Let's just do a quick unit check. Here's silver nitrate. Here's moles. We are left with silver chloride and grams, and we see that we have grams of silver chloride left at the end of our equation. Okay, one more example, and then you can go on your way to do some practice questions. A 200 ml sample of 0.221 moles per liter mercury 2 chloride solution reacts with 100 milliliters of 0.5 moles per liter solution of sodium sulfide. What is the mass of the precipitate formed? So the first step we have to do is we have to write out a balanced reaction. So mercury 2 chloride reacts with sodium sulfide, and it gives us, these are both solutions, and it will give us sodium chloride and mercury sulfide. If we look at our solubility chart, we will see that mercury sulfide is our precipitate and that it falls under slightly soluble. We still have to balance this whole equation now that we've balanced each compound individually. We have 2 chlorides here, and then we end up with 2 sodiums there, 1 sulfur, 1 sulfur, 1 mercury, 1 mercury. So this is now balanced. Write down our information that we have. 200 milliliters of 0.221 moles per liter, and we have 100 milliliters of 0.500 moles per liter, and it's asking us what is the mass of mercury sulfide that's created. So the second step is to find the number of moles that each reaction has. So 0.221 moles per liter multiplied by, make sure that our units are the same, and we'll get a value of 0.0422 moles for mercury chloride, and we will get 0.050 moles of sodium sulfide. We have to go back to the equation and we need to look at our coefficient relationship. So in number 3, we're going to see 0.0422 divided by 1, and we're going to see 0.050 divided by 1 to give us the same values. And what do we see? We see 0.0422 is smaller than 0.05, so this is the limiting reagent. Now that we know which one is controlling the reaction, we're going to go back to our original amount of moles, and I always go back up one step because if I get in the habit of taking this one, even though it's divided by 1, I will make the mistake and keep doing it in the future. So always go back to your original mole value. And now we're going to calculate out the quantity of mercury sulfide that we create. So 0.0422 moles of mercury chloride. Going to look at my mole ratio. This is step number 3. Mole ratio is that there is 1 mercury chloride to 1 mercury sulfide. And then step number 4 is to calculate out the mass. Now that I'm in moles of mercury sulfide, I know that mass is equal to N times molar mass. And the molar mass of mercury sulfide is 232.66 grams per mole. And I should get a value of 10.3 grams of mercury sulfide. When I do my linear check, I'm going to cancel out my mercury chlorides. I'm going to cancel out my moles. And I'm going to see that I'm left with mercury sulfide and grams in my numerator. That's what I ended up with, 4 units. You're going to stop the video and you're going to work on questions from pages 17 to 19.